file there that you're going to need. Down at the bottom, an Excel file. Maybe just right above the test room that I created, there is an Excel template file that I'd like you to get. Okay, so some announcements here. Homework 9, which is related to benefit cost analysis, is due on Monday, regardless of whether things are in person or not. Do you have a question?
Yeah, so if you do email the exam out and like we don't, like if you're going to warn us, obviously we're going to try to get to the best place with the internet, but like if we can't get access to the internet, I mean, what happens then?
I mean, you could pose a million what-if scenarios, and I mean, like, I don't know. You know, we'd figure it out. Okay. I mean, there will be a certain day that if we have remote testing, it would be best for you to drive to wherever you've got internet access. But, I mean, we're engineers. We'll find solutions and adapt, and we'll do it easier than most people. All right? All right. So, homework 9, due on Monday. We talked about benefit cost analysis on Monday. And just for review, why do we use benefit cost analysis? Why not just do rate of return analysis when we're talking about some of the projects that we instead evaluate by benefit cost? So concept review. Why this new method? Okay, it takes more into consideration than profits. Good. Because there's a lot of projects that aren't profitable but still need to be done. So they're not generating a rate of return for a company, but there are intangible benefits or benefits that are non-monetary that we somehow monetize to calculate these ratios. And then we, what's the decision criteria for B2C analysis? Anybody remember what's the rule?
1-to-1. For every dollar you put in, you get a dollar out.
Okay, that would be the minimum acceptable benefit cost, was $1 of benefit for $1 of cost. And so then the generalizable decision criteria is anytime the B2C ratio is greater than 1, then the project is acceptable. Today what we're talking about is what if there's more than one option? Then how do you pick which one is best? So greater than 1 is acceptable, but when you have multiple alternatives, we have to use an incremental analysis to select the best alternative. So any questions before we get into that new discussion for today's material? Okay, let's take 3 different possibilities for flood control. These are all pictures that illustrate flood control alternatives. One of them, if you want to protect people against flooding, is you build a flood wall. And that's something that we have here in Huntington. We have a flood wall. They're actually pretty rare. It's an unusual thing to be protected with a flood wall, but we've got it. Another alternative to protect people against flooding is to lift their home so that when there's flooding, the habitable floors are above the water line. So hopefully this isn't where they're going to leave it. I hope this is just them temporarily raising the house up with some wooden supports, and then they're going to build a more permanent foundation. But that's another alternative. A third alternative for flood control, and this is one that they use in New Orleans, is to have really big pumps that pump the flood water somewhere else. So you're just constantly getting the flood water out of the way to protect the low-lying areas that otherwise would be inundated. So we have 3 different alternatives, and sometimes we have to assess each one of them. First of all, for initial screening, we would just do an ordinary benefit cost analysis. And we would reject anything where the B2C ratio is less than 1 and potentially accept when it's greater than 1. But sometimes we have mutually exclusive alternatives. And mutually exclusive alternatives are options where you're going to only choose one of the alternatives, and you have to know which one yields the most overall benefit. So here is, just to refresh your memory, the B2C formula that we use in conventional terms. It's benefits minus, what is D? Disbenefits. And so those are the disadvantages having to do with delay or environmental degradation, or inconvenience or just whatever problems arise out of a project. So benefits minus disbenefits, and then in the denominator are the initial construction costs, which are generally provided in terms of a present sum, and then the operation and maintenance costs, which are usually annualized. So for us to combine these things together, we have to put everything in the same time frame. So remember, you have to find the present value of all of these amounts before you put it into the equation. Or you could find the annual equivalent of each of them and then combine them. But the time scale has to be the same for the amounts. This is the B2C equation, and what we're going to do is we're going to order these different alternatives, cheapest on the left, then more expensive, then most expensive. Hopefully that rings a bell, because we've done that similar ordering before when we did the incremental rate of return analysis. You're going to notice a lot of parallels between that, which we've done before, and today's incremental benefit cost analysis. The idea of comparing the cheapest to the next most expensive alternative is going to be what we do, where we calculate the incremental initial cost. So delta CI means how much more expensive compared to the cheapest option is the next option in line. So you look at the extra cost, both on an initial and ongoing basis. How much extra benefit do you get from the more expensive option compared to the cheaper option? And then how much additional disbenefit is there? So instead of this formula, we're going to rearrange it to where the incremental analysis is the difference in benefits between two options, the difference in disbenefits, the difference in costs, and all of that together gives us the incremental benefit to cost. So you'll do this comparison, and so for example, option A and option B. Maybe option B is more expensive. Let's say option B is $1 million more expensive than option A. But it provides $1.5 million in added benefits. Should you spend the extra $1 million to get the more expensive thing? If the incremental cost is $1 million, but your incremental benefits are $1.5 million, should you spend the extra amount? Yes. Anytime you can get $1.5 million in benefits for $1 million in costs, you should do that. Like if I opened up my wallet right now and I offered you $1.50 for every dollar you gave me, you should do that as long as you can. You should take that deal. And so the same thing is true in incremental analysis. What we're going to do is our decision criteria is whenever that incremental ratio is greater than 1, then the more expensive alternative wins in the head-to-head matchup of two options. And then that new defender is going to be what you use as the basis for comparison on subsequent analyses. So when the ratio is less than 1, then that means the extra spending isn't justified and the less expensive alternative is the one that you should select, assuming that it passed the initial screening, that its B to C ratio was greater than 1 to begin with, not the incremental B to C ratio. So you're only going to do the incremental comparison on the ones that pass the initial screening. So you'd throw out any option that in the original B to C analysis wasn't above 1. Okay, so that template file, do you have a question?
Is it like sort of similar to the incremental rate of return, except where instead of just looking at profit, we're looking at benefit?
That's right. Yeah,
Okay.
exactly right. So I gave you that template file. Let's see, I may have to download it also, unless... Yeah. All right, let me hand out... what we're doing is we're comparing 4 different options for flood control. And we know the cost of each option, the incremental cost. We know the incremental benefits disbenefits. In fact, there's 3 different categories of benefits. These flood control measures, that the dam is going to be useful in alleviating flooding and using for fire protection, and people can also enjoy recreation on the reservoir that this dam is going to cause. So what you need to do is add together the 3 different categories of benefits to find the sum of the benefits. So the handout explains what you need to do. First of all, step A, find the present worth of everything. And then step B, calculate the conventional B to C ratio for each alternative. And you can see off to the side that column that says conventional B to C in the second table in the template file. And then part C is the incremental analysis. And so I'll pause for a moment and allow you to get started on that, and then I'll bring up my solution, and we'll see if we can all get towards the figuring out which of these options is best. And here's a hint. It's not the one that has the highest conventional B to C. We really do need to do the incremental analysis to find the alternative that's best. So you should use the payment function. I'm sorry, let's see. No, present worth. So PV, and we're going to put the 75 years into the project life, and 0.06 for the MAR, 6%. All right, so PV function, reference the rate. And of course, I need to anchor that because I'm going to be dragging all around. Oh, I typed in 76. That should be 75. I'll change it in just a second. So the NPER, anchor the reference to the time. And then this is a payment. And the M&O, maintenance and operation, there's 75 of those. And so I'll put in minus and then reference that as a payment amount. So now I need to change that to 75. All right, so what this is saying is it's saying $52,000 a year for 75 years, discounted at 6%, is a present value of $855,704. So I use the PV function, and that recurring maintenance and operation cost went into the payment field. And then now what I can do is I can just drag it down through all the rest of them, and the only reference that's relative is the reference to the amount. The interest rate and the number of periods stays fixed at its original location because of the dollar signs. Now here in B, it should be the sum of those 3 different benefits. And so I can put that sum function inside of the present value function. So equals PV of rate, reference to the number of years, and then inside the payment I'm going to put the minus sign like I always do, and then in parentheses let's see if I can embed the sum function, the sum of those 3 things. So I'm saying take the present value of the total of those 3 things together, and so it's going to be the sum of the flood, fire, and recreation benefits all together.
That would explain why it's.
So it looks like all three of these options are potentially acceptable. Like all of them give us more value than cost. And the value is that it's providing flood protection because it's preventing flooding. This reservoir is a location, a source of water for fire protection. And so we can annualize those benefits. Every year that it's used to protect against flooding, every year it's protecting against fire, the annual value of recreation, and then we take it all to the present, find the costs, benefits, disbenefits, so all of them are potentially acceptable. Now, the incremental analysis isn't just one B to C ratio minus the other. What we have to do is a matchup, where the first comparison we're going to do is the cheapest versus the second cheapest. And so this is, the first matchup is B minus A. So B versus A is the first matchup. And what you should do is find the difference in cost, difference in maintenance and operation expense, difference in disbenefits and benefits, and then do the incremental analysis on these values, on the deltas, not just from the table above. Do the B to C of the deltas. And then you continue. The next matchup will be whichever one was better. So if B wins, it would be C versus B. If A wins, it would be C versus A. Same way we did the incremental analysis before, where you don't know all of the comparisons at the beginning. You have to go through them one at a time to know what the next matchup is. Okay, so I have the incremental costs, incremental benefits, and incremental disbenefits for B versus A. So I'm having the more expensive one minus the cheaper one. Now the delta BC isn't just the difference from up here. That's not what it is. I need to put these values into the B to C ratio formula. So benefits minus disbenefits divided by the sum of the costs tells me 2.57. Now that's not $2.57. That's not what that means. If you dragged sideways, it may have pasted the cell formatting to make it dollars. It's not dollars. This is a ratio. What it means is that the benefits are greater than the costs for B compared to A. And so the conclusion of this, if I kind of summarize the conclusion here, this shows that B is better than A. So then my next comparison is going to be C versus B. So B is my champion right now. C is the challenger. So C versus B. So I have the incremental costs, the incremental benefit, disbenefits. So then I say, let's do this. Benefit minus disbenefit divided by the sum of the costs. Okay, 0.96 means that if I spent the extra dollar that you spent to get option C instead of option B, for each additional dollar you spend, you only get 96 cents in incremental benefits. And so the conclusion is that since this is less than 1, that means C is not acceptable compared to B. C is overall acceptable, but on an incremental basis, it's not justified. It's not better than option B because you're not getting the full return that you need. You need to have more than $1 of benefits if you're going to spend $1 of cost. And so our final matchup is going to be B, which was the remaining champion out of the second comparison. So it is D versus B. And so I always mention the more expensive alternative first. So D versus B. Okay. And then let's one last time. I guess I could probably drag that formula down, but just for nice practice, benefits minus disbenefits divided by initial cost and maintenance and operation cost. Everything's been taken to the present. 1.12. So that means, option D is better than option B because each additional dollar in cost yields $1.12 in additional benefit. So, conclusion, which alternative is best? Option D is best. Now, this other question asks, what's the highest interest rate that could be used and still have an alternative that's acceptable? So here's the ones that tell us whether or not an alternative is acceptable. That's saying, what if all of a sudden money became more expensive to borrow? If we had to keep changing the interest rate and it's going up and up and up, what's the highest interest rate where you can still have an acceptable alternative? Is it 7%? No. We can go higher than that. Is it 9%? No. 15%? That's a little too high. 14%? So what we can do is let's do a goal seek. It looks like option B is the alternative that stays above 1 the longest. Data, what if analysis, goal seek. We want B to be set to 1 by changing the interest rate. And when we do that, and show a few more digits in the interest rate here, just so we can get some precision. Even if interest rates go up to 14.5%, we can still have a flood control option. Alternative B is still acceptable even if interest rates go that high. Okay, so what we've learned today is an application of the benefit cost analysis for comparing alternatives. These are alternatives that maybe wouldn't be acceptable to a private company because they don't generate profits. They generate benefits to society rather than profits for a company. But we go through the process of trying to put a dollar value on those benefits, and then once we've monetized the benefits and disbenefits, we do the incremental analysis one at a time to figure out which is the champion among all the options. That same process is what you need to follow in the homework. So if I do one last look at these announcements, remember your assignment is due on Monday. And then also I hope that you're making some progress on the project. All right, I'll see you in class on Friday unless we are on Blackboard Collaborate, in which case I will see your raised hands on Friday.
Ding, 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 ding.
That's right. Have a good day.